Thanks a lot to organizers for inviting me to this amazing place with so many interesting talks. So I will talk about chiral molecules and chiral discrimination with new methods. And I selected results which are, I think, equally applicable to amorphous chiral solids, so to materials to be a little bit closer to the topic of the conference. So first of all, I would like to, of course, thank my group and my collaborators. And so there are many people who contributed to the talk and to the ideas. Andres, David now left to, they have now independent careers in these places. Emilio and Margarita also in King's College, and Nicola and the new generation of students is here. And I would like to thank also my husband Misha and Piera Di Cleva for many years of collaboration. So, as I'm starting a new topic of a chiral molecule, let me introduce my favorite, absolute favorite chiral object, and this is the cow. So what makes cows chiral? This is the subject that two famous theoreticians, Jordan and Kronig, addressed in their Nature publication virtually 100 years ago. And what they noticed that cows, well, they first of all reported that cows are chiral, and second, what they noticed that they are chiral in the way they chew. So the jaw of a cow rotates in a certain direction, but the food goes in the direction orthogonal to the plane of rotation. So the typical chiral observable you can obtain if you take a scalar product of the food vector, so it's a current of the food, and angular momentum of a jaw. So because this is a vector and this is a pseudo-vector, the product is a pseudoscalar, and pseudoscalar is a typical chiral observable. So they are ideally suited, the pseudoscalars ideally suited for characterizing chiral systems because they change sign upon reflection or upon inversion. And of course, since the angular momentum can be written like this, you can also have a basic chiral measure as a triple product of vectors. Importantly, every chiral object has at least one pseudoscalar that we can address in our measurements. Now, more news, not only cows are chiral, we all are chiral. And this is because all the metabolic processes in our bodies are actually controlled by the imbalance between left and right molecules in our bodies. And what is interesting is that there are new investigations, new ideas reported that you can actually use the enantiomeric axis, which is the difference in the concentration of left and right molecules in biological liquids. You can use it to detect various diseases. So they can be very sensitive and even personalized chiral biomarkers. However, to detect these biomarkers, you need a combination of high precision and speed. And optical methods, they actually come to the fore because light is the fastest agent to interact with matter. And it's, of course, faster than chemical methods. But unfortunately, the precision of standard optical methods is not sufficient. So what is the problem? The problem is that in standard techniques, optical techniques of chiral discrimination, we rely on the helix of the circularly polarized light that this electric field vector makes as the light propagates. So the scale of chirality, as you can see here, is a wavelength. And if we look at these chiral molecules in our bodies, which are the chiral biomarkers, for example, serine amino acid, so they are extremely small, and they are a lot smaller than the size of this helicity. And here we're back to the problem that Kane elegantly pointed out that the chirality of this helix is really not well suited for probing chirality of this molecule. So if you look at it and you try to see what is the problem, you realize the problem is that the chirality, the helix that we have here, its chirality is non-local. And then you can ask a question, well, maybe we could think about local chirality, but that seems to be a counterintuitive concept because chirality is defined by the mutual orientations of different parts of the object, so it's non-local. Yet I can show you an example of local chirality. And what you see here is the electric field vector of the laser light, which draws a chiral Lissajous figure or chiral trajectory within a single cycle of evolution. So why is it chiral? Because this trajectory is chiral. Why is it local? Because this vector is hooked to a single point in space. Now, it's a non-equilibrium property because it is encoded into temporal evolution of any vector. But the vector, good news, is that the vector can be anything. It can be laser field vector, it could be induced polarization or current, it could be various vectorial observables. Now, what it means also that, of course, if we probe chirality locally, which means that we are not relying on the magnetic field, and that what makes our technique suddenly about 3 orders of magnitude more sensitive. Of course, once you come up with this idea of local chirality, you also need to come up with the idea how to characterize it. And here, cows really help because you can form a triple product. How? You take a snapshot of electric field vectors in 3 different moments of time. And then you form a triple product. If you see that this triple product is non-zero, it means that this trajectory came out of the plane during the evolution, this time period. Now, what you want to do, you want to take this product and average over the light period so that chirality is maintained on average. And then if you go, for example, to Fourier domain from here, just make a Fourier transform, you get this, what we call chiral correlation function, which you see here. And what you see that you have a triple product of 3 polarization vectors carried at different frequencies. So for the lowest order of this correlation function, you would need to combine light of multiple colors such that these vectors corresponding to different colors are not coplanar. So in terms of response of the matter, this correlation function corresponds to the strength of the coupling of this light to matter, and the strength of coupling is defined through these nonlinear processes. So it's a second order nonlinearity that is involved here, and you see there is interference between a 2-photon process and 1-photon process, and they end up in the same state, and that is why this energy, this frequency is the sum of these 2. And this is a simple example of a coherent control problem. We understand that the temporal shape is defined by the phase relationship between component, but also phase relationship between component control the interference here, which can be destructive or constructive, and it will be opposite for opposite chiral molecules. So what you have is that this chiral correlation function controls the strength of optical response, and you can form also higher order correlation function by taking more products, scalar products between field vectors at more time points, and they will characterize the strength of chiral optical response in the electric dipole approximation for multi-photon processes. I would like to mention even quickly that electric dipole interactions now explored very widely, and there are many new techniques, and I call it paradigm shift in chiral measurements or electric dipole revolution, and they all are based on the electric dipole approximation and promise a lot of increase in the enantio-sensitive signal. Now, What I told you before was that we can manage to control the handedness of light in every local point in space, which means that now we can also shape it in space. We can, for example, first option would be to do handedness such that it's exactly the same in every point. This light would be locally and globally chiral. But you could also take a different approach and shape it, for example, in such a way, and that was the idea of Emilio Pisanti, who came to my group and suggested this, and this is much inspired by his Nature Photonic paper, to create chirality vortex. So basically combine the locally chiral light that I just explained with the vortex light. And that's the setup that we came up with. So we have counter-rotating omega and 2 omega beams. Well, this is theory. And the orbital angular momentum of omega is 1, of 2 omega is -1. And then what we do, because we need to have a chiral Lissajous figure, we need 3-dimensional fields, which means that we need tight focusing. And then what happens is that the longitudinal component appears, also like Kane beautifully explained in his lecture. And then the chiral Lissajous figure in this case is actually like this. So it's a little bit like a knot, and it is chiral. Now the advantage is that you combine local chirality with a global property of topology. So this is how this particular light would look like if you look at it. This is the intensity, this is in the polarization plane. This is the correlation function that I have introduced before, and if it's strong, you see red, if it's 0, you see blue, and where it is strong, it means that the light is locally chiral all over these places. Now, importantly, the topological information or vortex information is encoded in the phase of this correlation function, and you see here a particular realization that we have is that the phase of this correlation function changes, for example, 6 times as we go around vortex from 0 to 2 pi, or from -pi to pi. So this phase encodes both the global topological information, because it is topological charge times azimuthal angle, and local information which comes from the local chirality of the Lissajous figure. Now we can also derive the topological charge for this light, and it's highly flexible. The input is orbital angular momentum of 2 omega and omega beams, and the spin angular momentum. Now, if you send this light to randomly oriented chiral molecules, such as mentioned in our case, and what we want to look at is a necessarily nonlinear process, because only via nonlinear process you can encode temporal shape into matter. And we particularly look at high harmonic generation, which Carlos introduced yesterday beautifully. So it does not matter if it's a high or low. For now, it's just important that this is a nonlinear response. And what I look at here is a near field structure that we get for right and left function. And what you see, of course, what is most clear is that you have 6 hotspots, the maximum of intensity. But if you look very hard, you will see that actually the images, this one and this one, they are rotated from each other. And indeed, if you look at the angle at which you have the maxima of the signal, you can show that in left and right molecules, the difference between this angle is exactly pi divided by topological charge. So this angle is basically the topologically protected quantity. Now we can also apply it to measuring figure of merit, which is interesting, for example, for testing these biomarkers, and this is the enantiomeric axis. So the difference between, in a mixture of left and right, the difference between left and right normalized by the sum. So what you want to do, you want to somehow benefit, at least we wanted to benefit from the topological character of this light, and we try to see if we can have robust enantiosensitive signal in addition to having sensitive signals due to electric dipole techniques. So what we looked at is the enantiomeric axis as a function, okay. So if you look at the far field image, you have a right function and left function, very similar picture. And if you look hard here, and that was before the same, that where you have maximum for left function, you have minimum for right function. It means that there is a kind of pi phase shift between them. If you look at the Fourier transform with respect to azimuthal angle, and you look at harmonic 6, which picks up this periodicity, you will see that due to this pi shift between them, you will see that for example, when the left function dominates, you will see the negative signal, and if the positive, and if the right signal dominates, then you see the pi shifted signal. So this step is what is particularly provided us with the robustness in measuring this enantiomeric axis, because you can see that if you are very close to 0, there is a very sharp response that you have a chance to catch. So what you see here in red is when we tried to check this, we introduced the noise, which was only available in our setup, with actually fluctuation of intensity, which was 10%, and we can see that the step basically is maintained. But then what we discovered was something different and a little bit disappointing, because we discovered that what can happen in the experiment extremely easily, that you don't have a perfectly circular polarized light. And you can have an admixture of a bit of a linear pulse, so your pulse is in the end elliptic, and what it does for our robust signal, it actually blows it up completely, because we have the appearance of new topologies. So if we stick into our topological charge amount of counter-rotating components, then on top of our -6 topological charge, we get -2, and to be honest, we don't see anything. So what we decided is that what is probably useful is to come up with the method in which you would be able to address these topological charges in a different way. So what we did is the following. What you can do in the experiment, you can change the phase between between two counter-rotating components. And if you do your measurement as a function of this phase, which corresponds simply to the rotation of the polarization ellipse, and then if you do a Fourier transform with respect to this phase and extract a specific harmonic, which in our case was harmonic 1, you see that you can recover the topological charge -2, and it again rotates. You are welcome to ask me more questions about it, because I didn't really explain why this happens, but I can answer it, of course, very happily. So now another point is when the light becomes elliptical, then another attractive property appears. It becomes globally stable, globally chiral, which means that we can have not only the vectorial observables, which is like the angle of rotation, but we can also have scalar observables, such as the intensity of the signal. And in this case, we can see 30% of circular dichroism, or chiral dichroism, better to say, for example, for harmonic 18 and harmonic 19. So now I very quickly switch to a different subject, and here the connection to quantum materials may be a little bit more evident. I would like to talk about spin chirality coupling, for the induced spin chirality coupling bypassing magnetic interactions. And I have to tell you about one more effect that I didn't mention before. So I will be speaking basically now about looking at electrons and looking at the photoemission process, and that's going to be super simple process. It will be just a photo effect. So one photonionization. So what Ricci figured out in 1976, and now this is a very, very famous effect in chiral methods, is the following: that if you take randomly oriented molecules and you come with circularly polarized pulse and you remove electron, and then if you put detectors such that they are along the propagation direction of your pulse, one in the backward direction, one is forward, what you'll discover that more electrons will go forward than backward if you have right molecules. But more electrons will go backward than forward if you have left molecules, which means there is a net current. This net current is enantiosensitive, and on top of it, it's really, really strong. The strongest measured was about 40% to the total signal. Calculations, you can get a lot more. So, and it's strong because it's electric dipole effect. Now, it's efficient probe, and that's why it's extremely interesting. So with my student Andres, some time ago, we wanted to express the current, this PCD current, in kind of simple terms, and what we realized that it can be expressed as a conductivity times the vector product of the components of the field, Fourier components of the field at the transition frequency. And the conductivity is, interestingly, is a flux of a certain field through a sphere in the K space, and this is basically energy shell. So the field, we call it propensity field, is simply a vector product of two photoionization dipoles, which connect the ground state with a given continuum state. What we found later is that the field is directly related to Berry curvature. Now I would like to connect a little bit to people who are doing materials, and I would like to point out the analogy between photoionization, in which we have a band ground state which is independent of K, and the parabolic band in the continuum, and interband excitations in solids. So here we have a conduction band, valence band and a conduction band, and if we're now going to send our circularly polarized photon, what we will discover is that actually the same thing will happen in both cases. So what you will find out is that there is a current which is very similar to PCD, but it's called circular photogalvanic effect. It was mentioned yesterday during the talk about topology. And in case if you have two, for example, bands only, in this case you can express it as a flux of the curvature through the sphere in momentum space. Here I have a movie which shows the physical origin of this effect. So basically imagine that the bolt is your chiral medium and the nut is the electron, and the rotation that you give to your system is the light pulse polarization. So you rotate the system and it responds up and down depending on its chirality. So it happens in amorphous solids, such as, for example, 3D Weil semimetals, but it also happens in chiral molecules, randomly oriented, that I'm talking about. And now what I want to ask is, what if we resolve this current on spin? So what's going to happen? We have certain geometric field. Its geometric origin is clear from this kind of analogy. And is it going to couple to spin? And how this is going to happen? So what happens is that you can, if you include spin and you resolve photoionization on spin, then you can introduce spin symmetric field and spin antisymmetric field. And spin antisymmetric is the one, of course, which is important for spin sensitive processes. Now, I'm entering the area of spin-resolved photoionization, and there is a lot of history to tell, and of course I will not go through absolutely everything. I will only mention a seminal work of Nikolai Cherepkov, who did absolutely all spin polarization, in fact, in one photoionization. The papers are very involved, and of course, because it's a Russian scientist and it's a Russian papers, it has absolutely no details. So you just have a formula right away. So, and there is an experiment that has been recently done in multi-photon regime and resolved on spin. So what we have done, we developed our approach, which is different from Cherepkov because it relies on the geometric fields. And on top of it, we repeated the results of Cherepkov to make sure that we have the same results were available. So now I'm ready to say what is the physical reason of spin polarization or coupling chirality to spin in this simple one photoionization process. I have to say that previous works basically, oh sorry, I'm going wrong direction. Previous works would not give you this perspective, and what is now possible is to say what is the role of geometry and what is the role of the dynamics. Okay, so first mechanism of spin polarization in the current is the dynamic mechanism, and dynamic means that ionization rate in the specific momentum k is simply different between spin up and spin down electron. Then the chiral quantity, the chiral pseudoscalar, which characterizes the strength of this coupling, would be the basically helicity of photoelectrons. So what you see here is the momentum times the quantization axis for this molecular system. So now when you convolve it with this, you basically find a situation of best balance between the best projection onto the sigma and best difference. And that maximizes your result, and that tells you what is the dynamics. So, okay, so it's driven by disparity in ionization rates. It features longitudinal spin current locking because the current is a long spin, and it is enantiosensitive due to helicity. Now, the second mechanism is geometric. And in this case, first of all, we see that current is going to be orthogonal to both detection of the spin, the x of the spin detection that you will use in experiment, and the propagation direction of light. So it's a transverse spin current locking. Now, the molecular pseudoscalar explicitly involves geometric field, which is antisymmetric with respect to spin. And you see that you have a transverse component of this field, which is orthogonal to k. And everything depends on how well this projects onto the spin quantization axis. And you again average over all k on your energy shell. So now we have the transverse spin orbit locking, spin current locking, and there is an interesting geometry which arises, which leads to left or right spin vortices. So now, once again, I forgot to tell you what is the pseudoscalar. So the pseudoscalar is, of course, here. You can see triple product, and this is the pseudoscalar, this detection axis, pseudovector detection axis, pseudovector geometric field, and vector k. Now, I would like to quantify these effects, but we did not really have any fancy code to do it. Result on spin, this is in progress. But we used a tool that we developed again with Andres some time ago. We came up with the electronic densities in hydrogen, which are chiral. And this is just a superposition of states in hydrogen with electronic density, which behaves like this. And you can use them for modeling, analytically modeling whatever chiral process you are interested in. And what we did here, we now repeated the same idea, but for argon atom, in which we looked at the superposition again for the same recipe of different orbitals of the argon resolved on the spin. And because so this is the initial state, and because the code is fully spin coupled, we can start with the state, these are two enantiomers, we can start with two states with the same spin but opposite chirality and see what happens. And in particular, explore these currents. So this is the first slide. It's a bit heavy, but good news that this is penultimate slide. So I told you about PCD, this very important effect in chiral spectroscopies, and it's known to be strong. So first we apply this state and its opposite enantiomer to see what is the strength of this current. And we see this as a function of k, momentum k, or maybe energy is easier to understand. And then what you see is that how it depends on energy. Here we have some resonances, funny resonances, but it does not matter. And you see that it can be up to 30% in this particular calculation. That also allows us to check that these are really chiral states because you see that it mirrors completely. Now we can look at the geometric mechanism, and remember it's a transversal spin current locking. And what you see in this case is the appearance of radial current. So that current was along propagation axis. This is actually in polarization plane, and it's accompanied either by left spin vortex or by right spin vortex. So the enantiosensitivity encoded in the direction of this vortex. Now, this is the geometric mechanism and its manifestation, and there is also the dynamic mechanism. The dynamic mechanism does not require circularly polarized field per se. You can do it with linear field. And then what you have are the two types. Well, it's basically the same type of current, more or less. I told you that it's longitudinal locking between current and spin, which means that you have current again in polarization plane, but spin is oppositely oriented to the current. So the current is red, spin is opposite. So that would be spin sink, and this will be spin source for one option. And the other option is that current can also go along the propagation direction, and again it can be either spin oriented the same way as the direction of the current, or in the opposite way, and that will be the difference between right and left molecules. And the signal, I forgot to say that in previous case, you can see that signal of spin-resolved current is also very strong. It's 20%. It can reach 20%, but say ballpark is 10. And here we also have a nice result, for example, for this current, about 10%, and a little bit less for the spin sink and spin source. So I would like to leave you with the conclusions. Thank you very much.